Dear students, I am Priyanjali Mukherjee, Assistant Professor of Electrical Engineering Department of Narula Institute of Technology. In today's video lecture, we will discuss on the construction of root locus for the systems which have the real poles. So, in this video, we will discuss two types of cases. One is the system which has the only real poles and there is no zeros, and another cases where the system has the real zeros. So, the root locus technique is actually introduced by the Evans and which is extensively used in the design of control system, and it is a graphical method for sketching the locus of the roots in the S-plane as the design parameter of the system is varied. That is, the locus of the roots of the characteristic equation when the gain is varied from 0 to infinite is known as the root locus. So, let us consider a system which has only real poles and it has no other zeros. So, the open loop transfer function of the system is given as Gs equal to k by s into s plus 2 into s plus 3. Here, the feedback is used as the unity feedback. So, Hs is given as 1. So, to draw the root locus, first we need to find out the number of open loop poles of the given system. Now, the number of open loop poles of this given system is 3, and these 3 poles are located as 0, -2 and -3 location, and it can be found out by equating this denominator part, that is equal to 0. So, the number of open loop poles becomes 3 and the pole locations are 0, -2 and -3. Now, the root locus is symmetrical about the real axis and the number of branches is equal to the order of the characteristic polynomial, that is the number of the poles of the open loop transfer function. So, here the number of root locus branch will be 3, and the 3 branches will originate or start at the open loop pole locations, that is 0, -2 and -3, and it will end at the infinite, because in this system there is no 0, and when there will be no 0, then the branches will originate from the open loop pole position and it will terminate to the infinite. Next, we need to check the point on the real axis which will lie in the locus or not. So, now if we consider the pole locations, so this is first pole at 0 location, this is second pole at -2 location, and this one is the third pole at -3 location. So, now if we consider any point between this 0 to -2, so from 0 to -2 for any test point, the total number of poles and zeros to the right hand side of the test point becomes 1, that is an odd number. So, all the points between 0 to -2 will lie in the locus, whereas if we consider any point in between -2 to -3, then for that any test point, to the right hand side of the test point, the number of open loop poles and zeros becomes 2, and that is the even number. So, any point in between this -2 to -3 will not lie in the locus, whereas from -3 to infinite for any test point to be considered, then it will lie in the locus. So, we can say that the point between 0 to -2 and -3 to -infinite will lie in the locus, and from -2 to -3 will not lie in the locus, and that's why the points between -2 to -3, this is represented by this dot line. Next, we need to find out the centroid and the asymptote. So, for asymptote, the number of poles is 3 and 0 are, there is no 0. So, n minus m, it gives, that is equal to 3. So, there will be 3 root locus branches that produce to the infinite to the asymptote with the angles, and the relation of asymptotes is given as 2q plus 1 into 180 degree by number of poles minus number of zeros. N represents number of poles and m represents number of zeros, and this q will vary from 0 up to n minus m minus 1. So, here n is 3, m is 0, and n minus m minus 1 is 2. So, the q will be varying from 0, 1 up to 2. And if we put these values of q here, so we will get an n minus m, that is equal to 3 over here. Then from this formula, we are getting that there are 3 asymptotes, which are actually this 60 degree, 180 degree and 300 degree. And next is the centroid. Now, the point of intersection of asymptotes with the real axis is known as the centroid. That means from the centroid, these 3 can be drawn. So, the formula of the centroid is given as the summation of real part of the poles minus summation of the real part of the zeros whole divided by the number of poles minus number of zeros. So, here the real part of the poles are actually 0, minus 2 and minus 3. So, summation of these 3 becomes minus 2 minus 3, that is minus 5. And here there is no real part of 0 because there is no 0 in the given system, and the number of poles minus zeros becomes 3. So, the centroid is coming at minus 1.667. So, at minus 1.667, we will draw the 60 degree line, that is the asymptote 1, another is asymptote 2, that is minus 180 degree, and another is 300. So, these 3 are the asymptotes that will be drawn from the centroid, that is minus 1.667. Next, we need to find out the breakaway points. Breakaway points are the points at which the multiple roots of the characteristic equation occurs, and breakaway points of the root locus are actually the solution of dkds is equal to 0. So, now we know that characteristic equation GSHS plus 1 equal to 0, or we can say that GSHS is equal to minus 1. So, we are putting GSHS, that is equal to minus 1. So, we can write that k equal to the minus s to the power 3 plus 5s square plus 6s. So, next we are derivating this with respect to s, and we are getting minus 3s square plus 10s plus 6 equal to 0. So, now we need to find out dkds equal to 0, and the solution of dkds equal to 0 gives us the breakaway point. So, if we solve this dkds is equal to 0, we are getting 2 solutions, that is S1 equal to minus 0.784 and another is minus 2.5485. Now, remember the any points which is located within minus 2 to minus 3 that is not lie in the locus. That means among these 2 breakaway points, this second breakaway point, that is minus 2.5485, is not in the locus. So, we will consider this first breakaway point as the actual breakaway point. So next we need to find out the intersection with the imaginary axis. So for finding out the intersection with imaginary axis, or it can be written as from the RH criteria table. So the denominator, from the denominator 1 plus GSHS is equal to 1, we can write down this equation, that is the characteristic equation, s cube plus 5s square plus 6s plus k equal to 0. Next, from this we need to find out the Rouse array, and Rouse array becomes this one, where s to the power 3 line is the 1 and 6, that is the alternative coefficient, and the second line is also the alternative coefficient, that is 5 and k. And from these two lines, the third line s can be calculated, that is 5 into 6, that is 30, minus k divided by 5. So like this way, which we have learned in the previous video, we can find out the route table. So after getting the route table, the criteria to this table is all the first column elements should be greater than 0. So we are getting two conditions, one is k greater than 0 and another one is 30 minus k by 5 greater than 0. So if we put the value k is equal to 30, then this line s becomes 0. So when all elements of route array become 0, then we need to find out the auxiliary equation from the previous line. So with here we will calculate the auxiliary equation, that becomes 5s square plus k equal to 0, and the solution of this gives the point of intersection with imaginary axis, that is plus minus k 2.449. So this is the complete root locus. So from here we can see that the four locations are at 0, minus 2 and minus 3. All the points between minus 2 to minus 3 is not in the locus, and the three asymptotes are originate from the centroid minus 1.667, and the asymptotes are 60 degree, minus 180 degree and 300 degree. So these are the asymptotes, and for this pole, when gain is varying, then directly it goes to infinite through this 180 degree line. So this is one locus, and another for these two poles, when the value is increasing, gain value, then both are going towards this breakaway point, that is minus 0.7847. And at this breakaway point, then it is changing its direction, and following the asymptotically angle, it will go to infinite, and it will cut the imaginary axis at plus j 2.449, and here this one cut minus j 2.449. So this is the complete root locus, which has three branches. One terminates to infinite through 180 degree line, and another two branches will terminate to infinite by following the asymptotically angle. So here we are considering another problem which has the system with zeros, and zeros are located at the real axis, but here we are considering that poles are not located on the real axis. So here we can find out in the same way the number of poles are 2, because the denominator has the order of 2, and the pole locations can be calculated by denominator is equal to 0, and for this solution we can use the formula of Sridharacharya, and we will get minus 2 plus minus j3. So this is one pole location. There are two poles, minus 2 plus j3 and minus 2 minus j3. So these are two poles, minus 2 plus j3, and this is minus 2 minus j3. And it has a single 0 that is located at minus 1. So number of open loop 0 is equal to 1, and 0 is located at minus 1. So according to the rules, there will be two branches, and among these two branches, the one branch will terminate to infinite and another branch will terminate to minus 1. And if we consider the points in between minus 1 to infinite, then to the right hand side the number of real poles and zeros is equal to 1, that is equal to even. So all the points in between minus 1 to minus infinite are in the locus. So next we need to find out the asymptotically angles. Now the asymptotes are those through which the locus will follow the asymptotically angle. So here the q becomes 0 because the q is varying from n minus m minus 1. Here the n is 2, that is the number of poles, and m is 1, that is the number of zeros. So n minus m minus 1, that gives 0. So as the q is equal to 0, so using the formula plus minus 2q plus 1 into 180 by n minus m, we are only getting one asymptote, that is along the 180 degree. So next we need to find out the breakaway point, and the breakaway point is the point where the multiple roots of the characteristic equation occur, and it is getting by the solution of dkds equal to 0. So using 1 plus dsh is equal to 0, we can find out the relation of k, and after derivating with respect to s, we are getting that dkds is equal to minus of s square plus 2s minus 9 by s plus 1 whole square, and comparing this is equal to 0, we are getting 2 points. One is 2.162 and another is minus 4.16. Now this point 2.162 is located on the right hand side of the j omega axis. So hence this point is not in the locus, because when we are getting that, then minus 1 to infinite was in the locus, and any points outside the minus 1 to infinite was not in the locus. So 2.162 is not in the locus. Next we need to find out the angle of departure from the open loop pole, because it has two complex poles, and for this we need to find out the angle of departure. So to find out the angle of departure, the formula is 2q plus 1 into 180 degree plus phi. Now this phi is the angle contribution from this pole to other poles and zeros. So first we need to join, first we are calculating the angle of departure from this minus 2 plus j3 pole. So we need to join all the remaining poles and zeros from this line. Then we will measure the angle from the reference 0. So this angle becomes 108.43 degrees and this angle becomes 90 degrees. So the angle contribution from poles to zeros becomes this angle phi of z minus phi of p, and so using this formula we are getting the poles are 198.4 degree and another is minus 161.57 degree. So this one is the complete root locus, and we can find out there are two complex poles, that is here minus 2 plus 3j and here minus 2 minus 3j, whereas the 0 is located at the minus 1 location, and from minus 1 to infinite the whole section is within in the locus, and any point that is not within this region is not in the locus. That's why it is represented by dot line. Now the pole locations, from these two pole locations there will be two branches, and among these two branches one will terminate to 0 and another will terminate to infinite along the asymptotical angle. So first we are considering the angle of departure for the pole 1, that is 198.43 degree, and remember that this angle should be drawn with reference 0. So we are taking this as a reference, and from this reference angle we are measuring this 198.43 degree, and at this angle the from this pole the branch is coming out. And for this minus 2 minus j3, here the angle of departure is minus 161.57 degree. So this is the 161.57 degree, and from this angle it will be coming out from the second location of the pole, and both of these will join at the breakaway point. And from this breakaway point, that is almost minus 4 point something, so this is marked at the breakaway point as minus 4, and from this breakaway point one locus is going to the 0 because its system has 2 poles and 1 0. So one branch is going to the 0. So this is one locus, and another locus will terminate to infinite along the 180 degree asymptotic line. So the green line shows another locus which terminates to infinite along the 180 degree line. So in this way we can find out the open loop poles and zeros of the system, and by increasing the gain we can find out the locus of the system, which gives the idea of the system stability. And the roots of the characteristic locus of the roots of characteristic equation, when we are varying the gain from 0 to infinite, we are getting the root locus, and using this root locus technique it gives the relative stability condition. So these are the references. Thank you.
Hope after this video lecture you have a clear idea about today's topic. Now we will go through some questions answer session in the context of this video lecture. Now you are requested to go through gradually and try to solve the MCQ questions by your own. Answers are also attached at the end of the each question.